So this screencast goes over the last couple examples that we didn't quite get to. A sequence is, sequence is just a list of numbers in a particular order. And we have a series is a list of numbers added together. We have an arithmetic sequence when the same value is added to each term. And then we have a geometric sequence when each term is multiplied by the same value. Okay. These are some of the formulas that you should be familiar with. You should also know that a series converges if the R value is less than 1 for a series. Okay, so let's take a look at an example here. We're looking at the infinite series 1 plus ln x plus ln x squared. The next term will be ln x cubed, ln x to the 4th. Okay, and the first thing that we're going to do is find the value of x so that the series converges. So for A, the first thing that we know is that we have a geometric sequence where u1 is equal to 1, that's our first term, and r is ln x, so that is our constant multiple. So the first thing that we want to do is find the value of x so that the series converges. So we know that a geometric series converges when the absolute value of r is less than 1. So what that means is that our r value, which is ln x, has to be less than 1. Now applying our absolute value knowledge, this means that ln x has to be in between -1 and +1. So let's take a look at those two inequalities. So the first one that we have is that ln x has to be less than 1. So what that means, I'm going to switch from my logarithmic form. Remember that ln is just log base e of x has to be less than 1. So now I know that e to the 1 has to be, let's do this here. Let's write it this way. So here we're going to say that x has to be less than e to the 1. If we look at the other side of our inequality, we've got that ln x has to be greater than or equal to -1. And here we can say that x has to be greater than e to the -1. So that is just changing from our logarithmic form to our exponential form. Okay. All right, so now I need to figure out when the series converges by combining those two. So then I would say, therefore, my sequence, I'm going to say series here, series converges when my x value is in between 1 over e and e. Part B is asking us to find the value of x such that the series converges into 2. I'm just going to add another slide in here so I can do part B. Okay, so we know that from our formula sheet, the sum of an infinite series is the first term over 1 minus r. So for our sequence, we had the same as before. Our first term is 1. Our r value is ln x. We want to find the value such that the sum of this infinite series is equal to 2. So let's substitute in what we know. Our first term, our u1 is 1. Our r value is ln x. This has to equal to 2. I'm going to rearrange this by saying that 1 minus ln x is equal to 1 over 2. So from here, I would get minus ln x equals minus a half, which would give me ln x equals a half. Using my same principles or same ideas to change this logarithmic equation into an exponential equation, I'm going to rewrite this as x equals e to the 1/2. And this just comes from the fact that ln is log base e of x. To rearrange this, I'm going to take the base of my logarithm and make that the base of my exponent. And then my answer is equal to the exponent right here. So now I know that this series converges to 2 when x equals the square root of e, which is just a number. Okay, let's take a look at our function example here, because we've got an example of composite functions. So we know from before that a function is a special type of relation where each input relates to only one output. Okay? Two command terms that you should be familiar with are draw and sketch. Draw means that you need a labeled accurate diagram. You should use a ruler, include your points, all those things. If the command term just asks you to sketch, then you should just give a general idea of the required shape. Include things like asymptotes, but you don't need to be as particular with your points or with your graphs. Okay. Domain and range using interval notation. We use brackets and parentheses. These square brackets facing out or open brackets mean the values are not included. A composite function, which can be denoted this way, or f circle g at x, helps with the idea of a chain rule. And then there's a relationship between inverse functions here. So let's do an example with some practice. We have two functions, f at x and g at x. And we're told that h at x, which is a third function, is f circle g at x. So the first thing I know is that f circle g at x is the same as f at g at x. So what I'm going to do is I'm going to write h at x. So I'll do a over here. And I'm going to put 1 over 2, which is my f at x. And I'm going to sub in 2x minus 3. So I put in, let's use some different colors. I put in my g at x right into the argument of my f at x, and now I just have a new function to work with. So I've got h at x equals 1 over 4x. Let's see. Got 2x minus 3, so I'd have 4x minus 6 plus 1, which gives me my function of 1 over 4x minus 5. So there's my h at x. The next thing that I'm asked to do is solve for the inverse. So in order to do that, the first thing that I'm going to do is put y equals 1 over 4x minus 5. I'm going to switch my x and my y. And now I'm going to isolate y. So first thing I'm going to do here is make my right-hand side not a fraction, my left-hand side a fraction, by switching the place of the x and the 4y minus 5. So I'm going to get 4y minus 5 equals 1 over x. Next thing that I'm going to do is I'm going to add 5 to both sides. My goal is to isolate y. And then the last thing that I'm going to do is I'm going to divide all of my terms by 4. So I'm going to get 1 over 4x plus 5 over 4. And then finally, I'm going to state using the inverse function notation, h inverse at x is 1 over 4x plus 5 over 4. So some algebra there for you, dealing with inverse and composite functions. Okay, so we addressed the linear and quadratic functions. The last one that we have to do is this rational function example. So just some terminology to be familiar with. First, we have the reciprocal function, where the numerator is any k, any constant, but we also have a rational function. That's where you have a function on top and a function on the bottom. In order to sketch a rational function, you should always look for the following behaviors. So you should find the vertical asymptote, which is our restriction from the denominator. Should also find the horizontal asymptote, which is a over c, which is really the limit as x goes to positive and negative infinity. Then we're going to find the y-intercept by setting x equal to 0 and solving, and then finding the x-intercept by setting y equal to 0 and solving, and then we're going to check the behavior around the asymptotes. So let's take a look at this example here. So first thing that I'm going to do is find my vertical asymptotes. So my vertical asymptotes is, let's write this like this. Got minus x plus 4. So my a value is 1. My b value is 1. My c value is minus 1. And my d value is 4. So my vertical asymptote is minus d over c. So minus 4 over minus 1, which means my vertical asymptote is x equals 4. Then I'm going to find my horizontal asymptote. Okay, which is going to be a over c, which is 1 over minus 1. So my horizontal asymptote is y equals minus 1. The third thing that I'm going to do is find my y-intercept. So I'm going to set x equal to 0. So I get 1 over 4. And then the last thing I'm going to do is find my x-intercept. So I'm going to set y equal to 0. So I have 0 equals x plus 1 over 4 minus x. Remember, when you have a rational expression that's equal to 0, or a rational equation in this case that's equal to 0, the only part that you have to consider is setting the top part equal to 0. Our denominator we know is never going to equal 0, so it's not going to have an impact on our solutions. So this is going to tell me that my x-intercept, there's only one of them. It's just x equals minus 1. So now, I'll add another slide here. If I'm going to graph this function, I'm going to draw in my x and y axes. Then I'm going to start by putting in my asymptotes. So I'll use green for my asymptotes. I have one asymptote at x equals 4, right here. And I also have an asymptote at y equals minus 1. The other two things that I know are my x-intercept and my y-intercept, so I'll plot those in red. My x-intercept, I got that backwards. My y-intercept is right here, which is, let's see, if this is 1, this is minus 1, that would be a half. So my y-intercept is right about here at 0.25. So I'm going to label that on here, 0, 0.25, or 0 and a quarter. And then I'm going to put on, let's see, 1, 2, 3, 4, 1, 2, 3, 4. My x-intercept at minus 1, got minus 1 and 0. And then I know, based on my experience with rational functions, that one part is going to be in this quadrant, and then the other part is going to sort of mirror that and be in this other quadrant here. And now I've got a graph of that function with all those key points on it, or key features.